In this structured question, a spring is attached to one end and hangs vertically with a cube hanging on the other end. So this is our spring, maybe tied to a ceiling or a scale, but we got a cube. So the cube is initially held so that the spring has 0 extension. So you put some hand underneath the cube so that it does have 0 extension. Okay, and then they give us the dimensions of the cube, weight, sides, and then the cube is released, then it sinks into the water. But then the cube reaches equilibrium with its base at the depth 7 cm below the water surface. So once you sink until 7 cm, you kind of stop there. Density of water given to us. Wow, it's a complicated setup happening here. Calculate the pressure difference exerted by the water on the bottom face and on the top face of the cube. So we are finding a difference in pressure. That sounds very much like upthrust force. So I'm going to redraw my nice block down here first. Okay, let's do it here. So I have a block. I'm going to take the side view. This block is, what's the height of this block? 5.1 cm. Okay, nice. Let's just write a 5.1 there. So this height is 5.1 cm. So pressure difference. How do we find the pressure difference? I think because of the whole thing is submerged in water, we can use delta P equals to delta rho GH. And then we know the height difference, right? So we can say, we say height difference. So it sink down to a height, up another height. So the pressure difference here will be rho G delta H, with a height change there. So the water is 1000 kilograms per meter cube. G is 9.81. Height is about 5.1 cm, but must convert to meters, okay? So 5.1 centi, 10 negative 2 is centi, and meters. Okay, so with this, we will get 500 pascals. So we can just write here 500 pascal. We already got pascal. Okay, so this one mark for final. 1 mark if you substitute, or you know the equation rho GH, to show that you knew this. That's 1 mark for you as well. Okay, so now that we have found that, the next part is we need to use our answer, pressure difference, to show that the upthrust on the cube is 1.3 meter. Wow, what's the definition of upthrust again? I mean, the cube is in water, so there's gotta be an upthrust force. Remember, upthrust is due to a pressure difference. On top of the block, there's a lot of mini forces due to the liquid pressing on it. Below is a higher pressure, so much bigger forces pushing up on the block. So if you take the big one down there and the small one up here, who will win? Of course, the one down here will win. So once you add up all those forces, you have a upthrust force kind of pushing upwards. And that is related to the pressure difference, all those small arrows. So we could try to use an equation, I guess. If you remember that upthrust is after derivation. Okay, remember we Miss Lee derived it in the earlier video. Rho Vg, volume submerged, times rho times g. But I say, Miss, what if I don't remember this equation? Okay, never mind. We will go back to the main definition then. So either use that, or if you remember that equation, or you can use the main one where force equals to pressure times area. Pressure equals to force per unit area, right? But in this case, you want to find roughly like the change in pressure. Change in force, kind of like that. Change in force is upthrust. So all this big force and all the small force, you can also use this method, okay? So if we use this is the upthrust. This will be 500 pascals times a cross-section area. What is a cross-section area? Okay, we got to look at our cube here again. So the cube area, I assume is a square. All sides equal and one side is 5.1 cm, right? So my area here will be 5.1 cm squared. That will be an area of a cube. And if I use this method, I will get 1.3 newtons. Okay, so this one, 1.3 correct, right? Correct. Okay, very good. Now you see, why don't we use the U equals to rho Vg if we know the equation? You see, they give instruction to use your answer in A. So they say use your 500. But this equation, I already derived the thing such as there's no difference in pressure there. So you could use this value. Don't know if the mark scheme will allow or give you marks for it or not. But just for information, you can use this also. You sub in 1000, 5.1 times 10 negative 2 cube times 9.81. You will also get 1.3 newtons. But no guarantee you will get any marks here. Because of the instruction, use your answer in A. They want to use pressure. So if you got force equals pressure equals to force per unit area or any variation of this equation, that's 1 mark for equation. And then you substitute in the correct values and you get the final one, that will be A1. The other method, I don't know, got mark or not. You have to go in gray area, I call that. Okay, let's move on to the next part. More forces incoming. So now that we have got the upthrust force, which is 1.3 Newton, let's also write it down. Calculate the force exerted on the spring by the cube when it is in equilibrium with the water. That's such a weird way to say it. Force exerted on spring by cube. What kind of force is that? Okay. Let's think of the cube. If I separate out just the cube, I think I'm going to do this. If I just look at the cube, what are the forces acting on the cube? Can draw, right? Can, right? Well, this cube will have weight, upthrust, and then a force due to the spring. We usually call that tension force or compression. I'm just going to put T. Then, if you look at the object of the spring itself, what are the forces acting on the spring? Well, the spring is attached to the roof, so I guess there's a tension force up there. There's also a tension force downwards that kind of pulls it. I guess the main focus that I want to bring your attention to is the relationship between this and this. These two are Newton third law pair. Force exerted on spring by cube is this one. On the spring, the block actually pull this spring down. But force exerted on the cube by spring is also this tension force. The same. So, although they want you to find this one, if we can find the one down there, we can basically say it's the same thing. So, we need to find the T. Alright, so if our block is in equilibrium, we got a bunch of forces there, we can kind of say that, since this block is in equilibrium, not moving at this point, equilibrium, all the upwards force equals to downwards force. So we can say T plus, what's our U? Yes, U equals to the downwards force. There's only one, so we're going to write there as W. So T is what we want to find. That will be W minus U. So weight is, what's the weight? They got to give, right? Weight. Weight is 4 newtons. Okay, very good. So 4 newtons over there. So 4 newtons minus the upthrust force, which is 1.3 from the previous. So this one, 4 minus 1.3 will give us 2.7 newtons. So right here, 2.7. And that's just 1 mark, unfortunately. No working mark. Okay. So this 2.7 is going to be our force on cube, which is also the force on the spring by the cube. They are Newton third law pairs. Alright, so now we go to the next part. The spring obeys Hooke's law. Hooke's law! Sounds so familiar. And the spring has a constant of K. So when I see Hooke's law, I see K, I'm thinking of F equals to Kx. I'm going to start writing that down first. Determine the initial height above the water surface of the base of the cube before it was released. Before it was released. Wow. Initial height above water surface from the base of the cube. So they are asking us, what is this height? How on earth are we supposed to find this height? I'm going to redraw these two pictures using the base of the cube as a reference, because they're using base of cube as reference point. So let's do it on this side. I'm going to need more space, man. Let's rub this off. Let's put in a nice tub of water here. There, nice and blue. Okay, base of cube in the beginning is out of the water lah. That's the base of cube. Got a spring. Actually, I know. We'll just draw this lah. Okay, this is the base of the cube, and there's no extension here. Then once you are in the water, you have extended all the way down until you are at what was the height again? 7 cm below surface of water. Okay, so let's write that down. Here is 7 cm. Now here's where we have to really crack our brains and think a little bit. How on earth do we find this height? My other question is, if we can find this whole height, then we can find the h. But what is this difference? This would be the extension of the spring. Because you see in the beginning, the spring did not extend at all. So extension is 0. Then the string become longer already, so it go down and some extension here lah. So can we find this x? If we can find this x, we can find a lot of things here. They give Hooke's law, they give spring constant. Okay, let's try that first. So the spring, once it go into the water, was stretched. F equals to kx. The force is the one up there, force exerted on the spring, which is a tension force. So this value got to come down here. So that'll be 2.7 equals to spring constant and then the extension. So how much did our spring actually extend? 2.7 divided by 30 is what? 0.09, right? 0.09 meters. 0.09 meters, or you could say 9 cm. But wait, that's not the final answer. This x, which is the difference from here to here, this one is 9 cm, which is the extension. Okay, I'm gonna write that side. X. So now we know that's 9. We got 7 to the surface of the water, so we can find the height, which is from surface up. So 9 minus 7 should give 2. So we're going to write that last part. So the height in the end would be extension minus 7 cm. So that will be 9 minus 7, giving us 2 cm. But your final answer, please put the 0.0. A lot of us we very happy we put 2. What a beautiful number. 2 SF. You must have at least 2 SF. So I'm going to write a reminder here. At least 2 SF. 2.00 is also okay. So this is a 3-mark question. Is it a 3-mark question? Yes, it is a 3-mark question. First mark is, do you recognize Hooke's law? Do you know what is Hooke's law? Did you use the equation? That's 1. So always start by writing the equation. Second mark comes if you found your 9 cm. That is the extension of the spring. But it's not the final answer. You want to find this h. So that's the last mark. Okay, so that's this part. Wow, this one very tricky. If in front wrong already, here also wrong a bit already. So this question is quite the killer. If you got the front part wrong, the last few parts will be quite hard. Anyway, what happened to our cube now? The cube in the water is released from the spring, free to do whatever it wants to do. Determine the initial acceleration of the cube. If I redraw the cube, it's going to look like this. Remember, we have the cube. We have tension pulling it up. We have weight pulling it down. And we also have upthrust. Like that. But the key point here is when it is released from the spring. So there is no more force due to the string pulling you up. No more tension force, no more Hooke's law. So I'm going to erase the T. So if just now they were balanced, now you're off balance. Now weight is going to be so much bigger than upthrust. So you will start to fall or accelerate downwards. Net force pointing down. So we got acceleration downwards. So when you see it's acceleration and force, let's start with force equals to MA. Okay. So this one will give us W minus U. Or rather, since this one W is pointing down, we call positive. Upward is negative. So we can say, W plus negative U equals to mass times acceleration. So the weight is 5 newtons. They give to us, right? Is it 5 newton or 4 newton? I lost track. What is the force? 4 newton. Oh, sorry, my bad. My memory a bit bad. 4 newtons. Right. 4 newton minus the upthrust, which we calculated here. Or they give to us a value even better. 1.3. So we got 1.3 equals to... They go give mass, man. They didn't war. They said the weight is 1.5. Sorry, is 4 newton. We need to find the mass. So we need to multiply by 9.81 here. And we can find the mass, which is 4 over 9.81. Can rearrange a little bit lah. So I'm going to write the whole number in here. 4 9.81 and then acceleration. So now you can find the acceleration and you should get about 6.62 meters per second square. It's about 6.6. I'm fine if you write 6.6 or 6.62 as long as it is 2SF. So 1 mark comes from the final answer. 1 mark comes from you realizing that, oh, must calculate the mass also. So must remember W equals to M, M equals to weight divided by G, the constant. Got write that, then okay already, yeah? So this cube very interesting. Now it's falling in water, falling. Now we need to describe and explain the variation, if any, of the acceleration of the cube as it sinks deeper and deeper. Well, why would there be variation? Isn't this constant? Aren't these forces constant? Well, okay, yes, this one we can assume this is constant. Weight we can assume is constant. But there is one more force that will appear as you fall or move through a fluid. That force is called drag force. Aiyo! So if you're moving downwards, accelerate down at first, so you have a velocity downwards. That means you will have, eventually, some kind of drag force that will get bigger and bigger. This is increasing. Yeah, something like that. So we need to do what? 2 things. Describe the variation of acceleration. Describe variation of acceleration. But you must also explain why do you say that. So how can we write this? If you haven't tried this, pause the video and try out and write some sentence and see if you can explain. But if not, let's try and explain what's happening. So we need to talk about drag force because that's the problem here. So drag force, or you could say viscous force, resistive force, sure, fine, increases as you begin to accelerate downwards at first. Increases as the sinking speed increases. That's our friend here. In AS, in the previous chapter, we looked at drag force roughly proportional to V square. Roughly thereabouts. It may vary slightly, but all you need to know is faster you move, the bigger the drag force that opposes you. So, what about the other forces? We haven't got to acceleration yet. Drag force is increasing. The other two, constant, right? Best to also mention, talk about all the forces here. So we can say weight and upthrust are constant. So the only thing that's changing is drag force. So since net force here, what is the net force? Downwards is weight, right? Upwards is upthrust, upwards is drag. So all this W and U is constant, it's just D is increasing. So since that one, the net force decreases, acceleration also decreases until 0 if it reaches terminal velocity. Okay, so we got our main ideas here. The 2 main ideas. The first one is if you talk about the drag force increases with speed. This is M1. Then you say Acceleration will decrease to 0. This is the A one. Okay, the weight and upthrust, that one in between, I just threw it in for extra good measure. Who knows, maybe got mark there. If this 3-mark question, confirm the third one will be from this idea of net force and weight and upthrust. So this is how you can explain. Quite an interesting question. Go look at it again. Take some time to brain it and try it again if you need to understand a little bit better. But that's all for this video. I will see you in the next one.